So you watched a video over the weekend, video 2.3. The link is still posted on my website if you need to view the video, but that kind of goes through the basics of polynomial long division and synthetic division. Today, we're going to look at what we can use or what we can know from polynomial and synthetic divisions. So the first thing that we talk about is something that pops up a lot as you progress in math. You keep hearing about something called the division algorithm. Okay, I'll give you a minute to write this down, the division algorithm. As you're writing it down, just know this. It's a lot of words to say something you already know. Okay, so this is the division algorithm. The division algorithm says, if f of x and d of x are polynomials such that d of x is not equal to 0, and the degree of d of x is less than or equal to the degree of f of x, then there exist unique polynomials q of x and r of x such that f of x equals d of x times q of x plus r of x. Okay. Now, they're choosing some of these letters. I think if you think back to division that you learned maybe in like 3rd, 4th, 5th grade, they're choosing some of these letters to match up to what we know in terms of division from those early school years. So f of x is really just like the main function. It's the thing that you're dividing. But d of x, they choose, is really your divisor. And if you remember the word divisor from those times you were learning about division, that's the thing you're dividing by. So the fact that d of x is not equal to 0 makes sense, because if you're dividing by 0, you'd have an undefined answer. Okay. Q of x is really your answer. So it's your quotient. It's the thing you get when you divide. And then r of x is your remainder. We'll do an example with polynomial long division on the next slide, but just to make sense of this and say, the division algorithm says really nothing new about division. It's everything that you always knew. I'm going to do a really easy example. I'm going to use a constant polynomial, so it has a degree of 0. And I'm going to say 17 divided by 3, where 17 is like my f of x, and 3 is what I'm dividing by, so it's like my d of x. Okay, and so f of x divided by d of x. If I did 17 divided by 3, you would tell me how many times does 3 go into 17? 5. 5 times 3 is 15. And when I subtract them, I get 2. So again, f of x is 17. 3 is my d of x. My answer, my quotient, is 5, q of x, and my remainder is 2. So if I put all those things into this division algorithm, I'm saying that 17 equals 3 times 5 plus 2. Do you agree? Yes. It all makes sense in terms of what you know about division from even elementary school. So the division algorithm has always been there. We've maybe just never stated it in this way before. Okay. And what we're saying is we can use a lot more complicated f of x, q of x, p of x, d of x, and r of x. And this still holds true. So let's look at an example with polynomial long division. Okay. Let's see. We have 6x to the 4th minus x cubed minus x squared minus 3 divided by x squared plus 1. Since I'm not dividing by just a linear factor, like x plus 1, I will choose to use polynomial long division. So I'm going to set up my polynomial long division. This is my f of x. What I'm dividing by, remember, is my divisor, my d of x. So we're trying to find the quotient polynomial and also the remainder polynomial. Notice I utilize that same a piece from the warm-up we talked about, like include the missing term. So I put a 0x in my f of x, just as a placeholder there for the x terms in case I need it. Okay, I do that with synthetic and with long division. And I'm going to divide by x squared plus 1. Whenever I start, I'm basically looking at just the first term of the divisor, x squared plus 1. What do I have to multiply the x squared by to get 6x to the fourth? 6x squared. So I find my x squared term, line up the 6x squared, and now I'm going to multiply that by my divisor, x squared plus 1. Don't forget to distribute. So I get 6x to the fourth plus 6x squared. Now, remember in division, you're always subtracting that. And when we have something that looks like polynomials, you're subtracting all of that. So change the signs of all the terms. This will really be minus 6x to the fourth and minus 6x squared. Do my addition or subtraction, I suppose you could call it there. 6x to the fourth minus 6x to the fourth cancels. Don't forget about this negative x cubed term. It's really like I don't have an x cubed to subtract, so it's just going to be negative x cubed. And then negative x squared plus negative 6x squared is negative 7x squared. And in polynomial long division, I usually bring down all my terms, just to kind of keep all the polynomial there, otherwise I kind of lose track of things. And then I start the process over. What do I have to multiply that x squared and x squared plus 1 by to get the same thing as what I now have down here, negative x cubed? Needs a negative x. So I'm going to put a negative x above my x term in f of x. I'm going to distribute that so that I get negative x cubed minus x. And remember, you're really subtracting that second line, so subtracting these negatives is going to make them positives. And do my combination. So I get negative 7x squared plus x minus 3. I've got one more to go because I'm not at the end for my quotient. I still have a constant term. What do I have to multiply x squared by and x squared plus 1 to get negative 7x squared? The negative 7. So I'm putting the negative 7 right above the negative 3. And then I'm going to distribute that. That will be negative 7x squared minus 7. Again, I'm really subtracting that second line. So if you were to do minus a negative 7x squared and minus a negative 7, that would turn into plus. And then we have x plus 4. So if we look at this like we looked at that example I did, 17 divided by 3, here's my f of x, here's my d of x, up at the top is my q of x, and down here is r of x. And the division algorithm would say that 6x to the fourth minus x cubed minus x squared minus 3. Thank you, guys. Have a good day. Is equal to my divisor, x squared plus 1, times 6x squared minus x minus 7 plus x plus 4. And so if we distributed x squared plus 1 over this trinomial, 6x squared minus x minus 7, then we added an x plus 4 to their like terms, we would come up with the polynomial f of x. So that's the division algorithm for the polynomial. We won't take the time to actually redistribute everything, but you could to see that it was actually the same thing. Okay. Okay, moving along. We want to talk about the remainder theorem then. So division algorithm says we can divide things as long as the divisor is not 0. When you take the quotient times the divisor and add your remainder, you get the thing you already had. Now we're going to look at what does that remainder do for us. Okay, so the remainder theorem says if a polynomial f of x is divided by x minus k, then the remainder is r equals f of k. Notice this theorem states specifically for dividing by x minus k, where x minus k would be a linear factor because it has degree 1. I think the key to the remainder theorem is understanding the then statement. Then the remainder is r equals f of k. When you say r equals f of k, you're saying the remainder is the value of the function think y at x equals k. So by dividing by that linear factor, we can find values of polynomial functions, y values, output values, for that x equals k. And so here's an example. Suppose we have 3x cubed minus 4x squared minus 41x plus 35. And we want to divide it by x minus 4. This one's a linear factor, so I might choose synthetic division. Okay, that usually would be, I would guess, our go-to polynomial division method. So I'm going to set up a synthetic division. Looks like I have all my terms in my f of x, so I don't need to worry about adding any zeros for missing terms. Got everything I need. And then remember, when you're dividing by x minus 4, you want to think about x minus 4 equals 0, so x is really 4. We're going to put that on the outside. And then I always say synthetic division is like repeating a little mantra to yourself: add down and multiply, add down and multiply. And you just do this over and over until you're done. So we're going to start by adding down. And then we multiply. 3 times 4 is 12. And repeat. Add down to get 8. Multiply 8 times 4 is 32. Add down to get, looks like negative 9. Negative 9 times 4 is negative 36. Add down to get negative 1. Now, the video that you watched over the weekend will talk about rewriting this as a quadratic. 3x squared plus 8x minus 9 minus 1 over x minus 4. And so that will, if you need to see that piece, how to write the new polynomial, you can. But what we're looking at is with the remainder theorem, this value at the very end, that's your remainder. And the remainder is equal to f of k. So what this is saying is that for f of 4, we're equal to negative 1. Meaning if I were to put 4 into this polynomial. Negative 1 would be my output for y. So that means that the point for negative 1 is a point on my graph of a polynomial. So if you're thinking about like an xy table, you have just found a function value, which is a y value, and you now know a point on the graph. We can also then use synthetic. Notice here we were dividing by x minus 4, and now we know that f of 4 is equal to negative 1. I can similarly ask you to evaluate a polynomial using synthetic division. So find f of negative 1. Find the function value at x equals negative 1 for f of x equals 4x cubed plus 10x squared minus 3x minus 8. And here we want to do it with synthetic division as opposed to what I would call direct substitution, where you just plug it in for x. If you want to find f of negative 1 using synthetic division, you really want the remainder, r. So I'm going to set up my synthetic work. Difference here is I already know x equals negative 1, so there's no change of sign. Like when you're given the linear factor, you can solve for x. Here we know x is negative 1. And we just work through synthetic. Whatever that remainder is going to be the value of our function. Add down, multiply, repeat. The number at the end is the value of your function. So we could say f of negative 1 is equal to 1. That also tells us, if we extend that, the point negative 1, 1 is on the graph. So using synthetic division this way can be really helpful, but if you think about the things that we've kind of been curious about in terms of our graphs, if you think back to that graphing exploration, we haven't really been paying much attention to like a whole lot of points on our graph. What are some points that we're really curious about in those graphing explorations? What points did we want to know? The zeros, which we would also call the x-intercepts. So we want to extend this information about the remainder theorem to figure out how can we use that then to find the zeros, to find the x-intercepts. Think about what your function value should be if you're on the x-axis. What are you looking for at the end? Emily? What? Oh, you were thinking like that? If you're on the x-axis, what should your y value be? Your function value. It should be 0. So remember in Algebra 2, we spent a lot of time doing synthetic division looking for zeros. That's going to bring us to our final two theorems. A polynomial will have a factor of x minus k. And then do you remember IFF? If and only if f of k is equal to 0. So you can identify factors, which factors produce zeros, like Kirsten was saying, we're interested in the zeros in the x-intercepts, if the function value is equal to 0. So we're going to put even more focus on that remainder, hoping for the remainder of 0. Okay, so here's an example. We want to verify a linear factor. So if I tell you x plus 3, verify it is a factor. That'll be step 1. Then use what you have from that to find the other zeros of your polynomial. Okay, so that would be, again, extending it one step further. Well, we know that x plus 3 would be a factor if and only if the function value at 3 was equal to 0. So we set up a synthetic. Notice on this one, I'm going to have to include 0 for x squared. And that would be important. Since we're checking the linear factor x plus 3, we want to check out a negative 3. Run through your synthetic, add down and multiply. I always put smiley faces in my zeros because it makes me happy. That means x plus 3 is a factor. Cool. So we verified it as a factor. How can you now find the other zeros? Anybody recall from Algebra 2? What do you mean keep going?
Let's do another synthetic division.
You could do another synthetic, and we're going to do that later this week when we do rational roots. But what else can you do with this stuff that's at the bottom? Because we don't have anything else to test, but we will, and you kind of know already, Catherine?
Get back into the formula and set y factoring.
Yeah. This is really, remember from division, you had taken an x cubed divided by an x, so now it's one less. It's x squared minus 3x minus 10. And so now you have a quadratic. Catherine says set that equal to 0. And then this could be something you could either factor or, if necessary, quadratic formula. I can factor this out as x minus 5, x plus 2. And so my solutions are 5 and negative 2. And so I could list all my zeros as negative 3, 5, and negative 2. So you spent a lot of time doing that in Algebra 2. And we are going to address the idea that Ethan threw out there of like, keep going with synthetic. We might need that if it's not cubic. Because if you start with a 5th degree polynomial, if you only divide one time, you still have something that's quartic. And we don't always know how to solve all quartic polynomials. So we might need to keep doing synthetic to get it to something we could solve. Okay? Okay, so just as a kind of review of everything we can learn from polynomial division. First of all, we can figure out the value of a function at x equals k. That's if you have linear factor x minus k. Do synthetic, the remainder is that function value. You can find factors. You can verify, you can find them. X minus k is considered a factor of a function if the remainder is equal to 0. That idea about a factor, again, still holds true from what you know about factors from elementary school. If I say, what are the factors of 15? You say 1 and 15, 3 and 5. You're only choosing numbers that divide evenly, have remainder zeros as factors. So the same is true in polynomials. And then finally, k0 will be an x-intercept. Kirsten called them zeros of the functions. Those are what we're really interested in if you think about our graphing explorations, if the remainder is equal to 0. Okay, so you can also identify your zeros. You can identify your x-intercepts.